Hello everyone. Tech good reads give you good thing to read to listen. Today I will talk about behind MySQL DB engine that data structures power the InnoDB and MyRocks. Here's today's topic. I will cover the MySQL architecture, InnoDB that using the B plus tree algorithm, and MyRocks using the SRM tree as a supporting algorithm, and the comparison between those two DB engines. Let's first see the MySQL architecture. For the MySQL architecture, it uses pluggable storage engines. We can see at the right side picture, MySQL is composed by several components. It includes MySQL connectors, shells. On the server side, include SQL and NoSQL interfaces, and also parsers, optimizers, caches, and buffers. For the storage engines, is used to store the data and include the memory management, index, relational and document storage managements. For the benefits of pluggable storage engines, it can help choose an adequate storage engine targeting a particular application needs, such as data warehousing, transaction processing, or high availability situations. Another benefit is that we can use a set of the interfaces and the services that are independent of any one storage engine. It's a platform providing those universal interfaces, while you can using the different storage engines for the different purposes. The most popular storage engine for the MySQL is InnoDB. It uses B plus tree as the algorithm. Here, I will focus on the primary index, how it's implemented. For the InnoDB, it uses B plus tree. And the data structure is look like the right side of picture. We can see it's the tree, and each B tree node is compared with the keys and pointers. The pointer may be pointed to another child level of the nodes, and at the leaf node, there are pages. The pages containing the key value pairs, that's the primary key and the data stored there. This B plus tree algorithm allow efficient key value lookups and range queries. For each page, it has a fixed size. It may contain different number of the key values there. And for the internal node of the tree, it contains keys only and pointers to the other child nodes. For the data, it's only on the tree leaf pages. And this kind of structure is called clustered index. It means that the data is stored with the key at the same place. Such clustered index is very efficient to read the data because when you reach the leaf pages, you can get data from there directly. One question is why the MySQL chooses the B plus tree as the supporting algorithm. Now let's think about other possible solutions. For such key value pairs, we want to get the value efficiently. So one way we can think out is that why we not use the hash indexes. For such a hash map in the memory, it's very efficient to get the data. It's just O1 computational complexity. But for the MySQL, in memory is not enough. So the data must be persistent to the disk and read back. In this way, it's difficult to make an on-disk hash map perform well. because like on disk is the random access I/O, which is not efficient. Also, for the hash indexes, the range queries are not efficient. Since hash index is not optimal, we may think out that we can make the key sorted. In this way, we can use similar architectures as the binary search tree or balanced BST. But for the binary search tree, the worst case of that is a linked list. That's the ON. This means that the performance is not stable. If we use the balanced BST, we can achieve O log n. It means that I/O request to the disk to read that data. And this means one data, we need too many I/O requests there. And also when we read data from the disk, only one node of the data is transferred in an I/O. That's not efficient. In this way, B tree solves the BST problem. The difference between the B tree and the B plus tree is that the B tree stores the key and the data at the same place. This means that internal nodes on the B tree also contains the data. Thus, when we want to do any search on the B tree, it need also query that the internal nodes, especially for the range queries. Since the data distributed all over the trees, it needs random I/O access for the disk to get that data. But on the B plus tree, since all the data are on the leaf nodes, we can use pointers from one data to the next, and then we can do range queries to get those data efficiently. The next storage engine I want to talk about is MyRocks. It uses the SLM tree. MyRocks is the RocksDB usage adapted to the MySQL, and this is invented by the Facebook. Let's see the MyRocks architecture first. The algorithm is called the log structured merge tree. The abbreviate as the SLM tree. When we do any data write, it first write a mem table. This table is in the memory and is sorted key value maps. When this map table is full, then that data will be immutable and then flushed into the disk. The disk file is also sorted and is called sorted string table. Since such a SST may contain the duplicates in the different level, then we can compact those SST files into an older one. Thus that SST has different levels. We can see that it contains L0, L1, L2. And also, since the data is written into the map table, if the server crashes or restarts, then there may be data loss. So when I read, it not only read to the map table, but also read to read ahead log. Read ahead log is used for the data recovery. For a read, it first reads the data in the map table. If it's not exists there, it will go to the L0 SST tape file. If not there, it goes to L1, L2 until all the SST files are scanned. For the map table, it's an in-memory sorted map. To implement such a sorted map in memory, we can use a balanced BST like a red-black tree, AVL tree, or skip list. Since skip list is very easy to implement, so most of the algorithm tree use skip list to implement such a mem table. It provides O log n search complexity. When such a mem table is full, it will dump to the disk access table. For the sorted string table, it's dumped from the mem table, so it's also sorted key value maps. When we have too many sorted string tables, we can merge them together using the merge sort algorithm. It's a very efficient algorithm to implement such merge and compact. This can help reduce the space needed. But we can also see, since too many levels of the access table, read requests need to scan over several segments. Let's compare those two storage engines. This test data was executed by the Facebook to compare the InnoDB and MyRocks. We can see that MyRocks using a much smaller space and less bytes written per second compared to the InnoDB. So these two storage engines, since their algorithm was different, it provided different features. For the B plus tree, it has a problem called write amplification, because that each time is updated by page, and the page will be persistent to the disk. If we have any random write for the index, it also needs to be persisted. It also has a double write in the implementation, because that bin log and redo log need to be written at the same time. Also, more logs causing more writes. Also, in each page, the page is a fixed size. So in the pages, it may be fragmented due to the different item of the key values, and the whole page is not fully used. This means that InnoDB compression is not efficient. But InnoDB has a very good read efficiency, because that B plus tree for the search algorithm is very stable. For the RocksDB, that's supported by the SRM tree, it has a better write amplification, because that using the write head log to append the log only. It don't need a random write. Also, for the SS table, it's append only, and also for the compaction, it's a sequential write. This means that it writes has a much smaller number compared to the InnoDB. Also, for the algorithm is log-based, its compression is very efficient, because it's append only. There's no fragmentation in the data. But we can also see that it has a problem of read amplification, because when reading a data, if it's not in the mem table, it needs to check several access tables at different stage of the compaction. That's all for today's content. If you need a further understanding of those storage engine, you can refer Designing Data-Intensive Applications, that book, also MySQL, MyRocks websites. Thank you for listening. This is Chinese. See you next time.